Hey guys, this is another video on the 9 common techniques for rewriting integrands so that our basic rules apply. This is the first of the techniques. It's called expanding a binomial or trinomial. So here's an example where you might use this. Maybe you've got something that looks like this. And you are asked to antidifferentiate it. Now, because of the parentheses, I might be tempted to use u-substitution. It looks like it might be a u-sub because I've got all of this inside another function, and we know that we use u-substitution anytime we've got a function nested inside another function. But u-substitution doesn't work this time. Notice also that your basic rules do not apply. Because I've got this expression squared, and unless it's just an x squared, I don't have a rule like that on my list, or a secant squared, or a cosecant squared. Those are the rules on my list that involve squared functions. They don't look anything like this. So I go through my checklist. Basic rules do not apply. And u-substitution doesn't apply. If it did apply, u would have to be this entire inside function. Remember, whenever you're doing u-sub, you're looking for a function nested inside another function. And then we have to be able to write everything up here, including the dx, everything in terms of u, with no x's left. And that's not possible in this case. So just to show, let's say we are trying the u-sub. If I were to try u-sub, u would have to be my inside function. That's the function inside these parentheses. This is a function squared, so that's a natural choice for u. If this is my u, or if it is a u-sub, that's probably the u. So I write that down, and then I need to take its derivative. Now remember, this square root of x is actually an x to a different power. That 5 is just a constant. Now, you may have forgotten this rule. Probably been a while since beginning algebra. If you're taking the nth root of x to the m, that can be written as x with a rational exponent. It's x to this power divided by this power. So whatever that index is, the index of the root that's right there, that needs to go in the denominator. Now this is just like this. It's a little less clear though. If there's nothing over here as an exponent for the x, we have to assume that there's a 1 there. And for any root, third root, fourth root, fifth root, that number is going to be right there, except for the square root. With the square root, it's implied. There's an implied 2. So that's an x to the 1 over 2 power, or x to the 1/2 power. So here's an example. If I have, well, let's say the fourth root of x cubed, that's x to the 3/4. Or if I have the square root of x cubed, you have to remind yourself there's an implied 2 there. That's an x to the 3/2. Square root of x, a little less clear, but there's an implied 1 there and an implied 2 there, so that's an x to the 1/2. So that's what we're doing. We write that this way first, and then we take the derivative because we're trying to see if u-sub will work. The derivative of this is, well, 3 times 2 is 6. We bring the x down, multiply by x to the 1 less power. 2 minus 1 is 1. Then you bring your 5 down, bring the exponent down, and multiply by x to the 1 less power. 1/2 minus 1 is 1/2 minus 2/2. 1 minus 2 is -1, so that's a -1/2 power. And don't forget, all of that is multiplied by dx. So I've got a 6 minus 5 over 2 times x to the -1/2 dx. Now remember, we can only do a u-sub if every single part up here can be written in terms of u using this. So I need this 6x times 5 over 2 x to the negative 1/2, that maybe times a constant, to be up here somewhere in order to use this, in order to do a u sub, in order to take care of that dx over here. And we don't have exactly that. We don't have a 6x and a 2.5 times x to the negative 1/2, so the u sub isn't going to work. Don't think of this as u squared du, because it's not. That is not du. dx is actually that all divided by that, and that's not going to work. So u sub fails. U sub fails because I don't have a constant times this as part of my integrand. So I'm going to have to do something else. Okay, so that's when our 9 techniques come in, excuse me. So our basic rules don't apply. U sub doesn't work. Then I go to my 9 techniques. And the first of my 9 techniques says, if you've got a binomial or a trinomial and it's squared and a u sub doesn't work, just square it. And then after you square it, use your basic rules. And that will work in this case. So I'm going to write this twice. And then FOIL. Remember that square root of x is an x to the 1/2 power. Still don't have a rule for that, but if I FOIL, I do have rules for all of those terms. First times first. Remember, multiply the coefficients first. That's going to give you a 9. X squared times x squared is x to the 4th. You're adding the exponents. It's first times first. Outer times outer. Multiply the coefficients first. 3 times negative 5 is negative 15. And then multiply the x's. X to the 1/2 times, or x to the 2nd times x to the 1/2. You may have forgotten this rule from algebra. You add the exponents. So that's x to the 2.5. Or if you prefer a fraction as an exponent, and we usually do in calculus class, that's 4 over 2 plus 1 over 2. So that's x to the 5 over 2. Because here's our rule. X to the n times x to the m is x to the n plus m. Add the exponents. So that's outer times outer, inner times inner is exactly the same, so we just write that down. And then last times last, negative 5 times negative 5 is positive 25. And then you add the exponents here. X to the 1/2 times x to the 1/2. 1/2 plus 1/2 is just 1. So we get that. And then we've got a couple of like terms there. It's always going to happen. When you square a binomial, you'll have some like terms. Negative 15 minus 15 is negative 30. And we've got rules for all of this. So we'll just apply our basic rules now. Now remember, whenever you're taking the antiderivative term by term, you're going to pull the constants down. Then you're going to add 1 to the exponent and divide by the new exponent. Bring that negative 30 down. Add 1 to the exponent. Since that's a 2 in the denominator, instead of adding 1, I'm just going to add 2 over 2. Because 1 is the same as 2 over 2. 2 over 2 plus 5 over 2 is 2 plus 5, so 7 over 2. That's my new exponent. And then I divide by the new exponent. Every time you divide by a fraction, remember it's multiplying by the reciprocal. Dividing by 7 over 2 is the same as multiplying by 2 over 7. So I'm going to put that there. I'll do my algebra a little bit later. Then bring the 25 down. Add 1 to the exponent. Divide by the new exponent. Don't forget your plus c. That's our answer. It's just not simplified. This guy, to clean that up, you might write that as a 30 over 1, and then just remember when you multiply fractions, you multiply straight across. So I've got 9 over 5 times x to the 5th minus this constant times x to the 7 over 2 plus this constant times x squared plus c. Now I know that some of the problems in the book and in the exercises aren't this complicated, but I want you guys to get used to practicing your exponent properties because it comes in handy when we study sequences and series later in this course, and in Calculus 3 and in differential equations. It's important that you learn algebra before you go on to the big university. So that is one example of where I would square a binomial or trinomial. Here's another one. Now this looks a little different. But it's almost exactly the same. It just involves exponential functions. If this was my u, du would be a 3e to the 3x minus 8e to the negative 2x. By the chain rule, that all times dx, I don't have the derivative of this as a factor up here somewhere. Since I don't have the derivative of this inside function as a factor of my integrand, u sub is going to fail. If you don't believe me, you should go through and practice and show yourself that the u sub won't work. But I see that I've got a binomial expression or something close to binomial. It's got two terms and we're squaring it. So we're just going to write it twice in FOIL. This is another good opportunity to practice our exponent properties that are so important in Calculus 2, especially if you want to get the right answers. Okay, first times first. E to the 3x times e to the 3x. It's that same rule from before. I know it looks different because of the e's, but if those bases are the same, you just add the exponents. So if I have e to the 3x times e to the 3x, keep the base, add the 3x and the 3x, so you get e to the 6x. Outer times outer, there's a 1, and implied 1 in front of that, so I've got a 1 times a 4, that's 4. E to the 3x times e to the negative 2x. Add the exponents, 3x plus negative 2x is positive 1x. That's first times first, outer times outer, inner times inner is exactly the same. Last times last, do the coefficients first. 4 times 4 is 16. Then add the exponents. E to the negative 2x times e to the negative 2x is e to the negative 4x. And then we collect like terms. And I don't know why I used a bracket there instead of a paren, but I guess I just felt like it. I've got 4 of those and 4 of those, so together I've got 8 of those. All right, now we're ready to apply some basic rules. Now, you may have forgotten, but here's just a reminder from Calc 1. The rule for the antiderivative of e to the x should be your favorite rule. It's the easiest. It's just e to the x plus c. Turns out the derivative of that is the original function itself. It's very, very cool how the slope of the function is actually the function value. That's one case. Now, that's going to work for this guy, but it doesn't work for this guy or this guy. In order to do these, I've got to take care of that constant in front of the x. So if you have a constant in front of the x, here's our kx modification. You're going to write the exponential down. Now, that's not the right answer. It's close to the right answer, but it's not the right answer. Let's think about why it's not the right answer. If I take the derivative of this, I should get this back, because this is an antiderivative. The antiderivative of this is this, because if I take the derivative of this, I get the function back. Differentiation and antidifferentiation, they undo each other. So when I take the derivative of this, I should get this back, but I don't. If I've got a constant times x here, the derivative of e raised to a constant times x is e to that power times the derivative of the inside. So I'm taking the derivative, I multiply by the k. So for example, I'm taking the derivative of e to the 3x. I get e to the 3x, and then I multiply by the derivative of the inside. So I multiply by the 3. Not 3x, I don't know why, but for some reason a lot of students have been doing 3x lately. It's not 3x. The derivative of the inside is just a 3. And we'd be done. Now when we're taking the antiderivative of e to the kx, I'm just undoing that. With this one I multiplied by 3. When I antidifferentiate, I better divide by the 3 to undo that. So whenever you've got a kx inside, the antiderivative is e to that power, and then you divide by the k. And then don't forget your plus c, of course, because the derivative of this is e to the kx times k. K over k is going to be the one that you have out front here. So that's what we're going to use for all three of these guys. Oops, actually I don't need my antiderivative anymore. No more integral sign because I'm about to apply my rules. As soon as I apply my rule, my integral sign is gone. So I've got e to the kx. K is 6. So I have e to the 6x. Don't forget to divide by your 6. Bring the 8 down. Antiderivative of e to the x is e to the x. Bring your constant down, 16. Then with e to some power, you're going to get e to that power. If that's a kx, don't forget to divide by the k. And of course, don't forget your plus c. So that's our answer. It's just not simplified. So I've got 1/6 e to the 6x plus 8 e to the x. 16 divided by -4 is -4 e to the -4x plus c. There you go. And so we're done with that. Okay, one more. Now this is not just this rule, it's this rule combined with a different rule from another section. But let's say you had this. Now, this would be a very tempting problem as far as u-sub is concerned. That looks like a u-sub, but it's not a u-sub. It really isn't. And I'll tell you why. First of all, we've got to ask ourselves if basic rules apply. Always ask yourself if basic rules apply first. Do I have a rule for that? No, I don't. So I've got this quotient. We don't have a quotient rule for antidifferentiation unless it looks exactly like 1 over x or 1 over u, or it looks like one of the other rules on our sheet. And it doesn't. I've got this expression squared divided by y, so that's not going to work. So basic rules don't apply. Always check that first. And u-sub doesn't apply. Now in a problem like this, I've seen many students try to apply it. They say, are you sure it doesn't apply? That should be my u. What's the derivative of that? It's 2y, right? And there's a y right there, so why doesn't it work? Let's be careful. So let's say we're trying u-sub. If I were to do a u-sub, u is an inside function. It's a function nested inside another function, usually under a radical, in parentheses, under, or maybe it's the entire denominator. Maybe it's inside a trig function, inside an exponential function, but it's inside something else. So the clear choice for u is this y squared minus 2 because it's in parentheses. So I'm thinking to myself, that's probably my u. Let's compute du. Du is the derivative of this times dy. Do I have that? You might say, yes, there's a y dy, and we don't care about the 2. You're right about not caring about the 2. I can always multiply or divide by a constant to get rid of the constants. I am concerned about the y dy, though. I don't have a y dy. It looks like you've got a y dy, but that's a 1 over y dy. Do you see it? This y is in the denominator. Since this y is in the denominator, if I were to pull that out as a factor, that's a 1 divided by y times dy. It's not just a y dy. So u sub fails. U sub's not going to work. We're going to have to do something else. And I see this binomial squared. So the first thing I'm going to do is apply my first rule. I'm going to expand that binomial squared. First times first, remember we add the exponents. It's y to the fourth. Outer times outer is negative 2y squared. Inner times inner is exactly like it. So it's going to be negative 4y squared when I add those together. Last times last is 4. We're taking all of this and dividing by y. Now you might say you still don't have a rule for that, and you're absolutely right. But there is a little bit more algebra that we can do that will allow us to apply our rules. This is just a monomial. It's just got one term in the denominator. So what that means is if I take this polynomial up here, or if I want to divide this polynomial up here by this y, all I have to do is take each term, this divided by y, and then this divided by y, and then 4 divided by y. And it's going to be exactly the same thing. Now if that was a y plus 2, I could divide every term by y plus 2 and that'd be fine, but I can't divide it by the y and the 2. We can't split up the denominator, but if the denominator has one term, we can split up that numerator. All of this divided by y is y to the fourth over y minus 4y squared over y plus 4 over y dy. And just to justify it, and this might be overkill, sorry if this is very easy for you and it's very clear, but just in case it's not, for those students that it's not clear for. You know when you add fractions, you do something like that, 1/3 plus 4/3, as long as the denominators are the same. We're talking about the same piece, the same size piece. So I've got 1/3 of a pie plus 4/3 of a pie. How many thirds do I have? I've got 5/3 of a pie. I keep the denominator the same, and then I add the numerators. So in general, if I've got a over c plus b over c, all I'm going to do is keep that denominator the same and add the numerators. All I'm saying here is that I can do that backwards too. If this is equal to that, if 5/3 is equal to 1/3 plus 4/3, well, I can split that 5 up any way I want. I can take that a plus c over, or a plus b over c, and I can write it as a over c plus b over c, because that's just how we add fractions with like denominators. So this is legal. I can take every term and divide it by y, and I'd be good to go. We've got to use more exponent properties again. We have used the fact that x to some power times x to a different power is x to the sum of those powers. Here we're going to use another rule, the division rule. I'm going to take the power in the numerator and subtract the power in the denominator. It's because that's the number from the numerator that are going to cancel. So here I've got y to the fourth over a y, that's an implied y to the first. One of those y's is going to cancel, and I'm going to be left with a y to the third. Or you can think of it as applying this rule. 4 minus 1 is just 3. Bring that down. Now over here, if you have a constant, you want to factor out that constant. The constant this time is a 1 over 4, or a negative 1 over 4. So bring that down. Y squared over y to the first, subtract the exponents, that's a y to the first. You could write the 1 if you want to. You don't have to. Remember, it's not a prime. It's just to the first power. And this 4 over y, it's tempting to write it as a negative exponent, and sometimes that's appropriate. But in this case, I'm not going to write it as a negative exponent. I'm going to think of this as a 4 over 1 and factor out the 4 and then multiply by 1 over y. And you might say, why on earth would you do that? It's because I have a rule for this. Now some people see this and they immediately see 4 times the natural log of the absolute value of y. If you're that person, you don't have to show this step. But for those that are unsure, for those people that see that and they can't match the pattern because of the 4, pull out the 4 and you'll see that you've got a rule for that. Now some people will still say, Miss Townsend, I'm not 100% sure that that's algebraically equivalent to that. How on earth did you factor out that 4? Well, remember, this is a 4 over 1. And I'm multiplying it by a 1 over y. If I multiply straight across, I get exactly what I had up here. The only reason I'm doing this is so that it looks more like my rules. And the only reason I'm doing that is because sometimes I need it to look almost exactly like my rules to remember that my rule applies. You might not need to do that, but that's there for those people that do need to do that. So factor out your constants, and then just apply your basic rules. So we're going to add 1 to the exponent and divide by the new exponent. Dividing by 4 is the same as multiplying by 1/4. I'm going to bring down my -4. Add 1 to the exponent, divide by the new exponent. Bring down your 4. Antiderivative of 1 over y is natural log of the absolute value of y. Don't forget your plus c. That's our answer, it's just not simplified. 4 over 2 can be simplified to a 2. Alright, so that was expanding a binomial squared, and then we divided each of these terms by a y. But you'll see more examples of that in the next video.